Okay, class, I realized where I screwed up the last time and paused it. Um, that's okay. It was right at the end of the third lecture. And so what I'm going to do is just go through those extra things one more time. In fact, it'd be the first time for you. It'd be one more time for me. So anyway, let's get back to it. We've got a lot of material to cover. And you're going to learn a lot of new mathematics that you really haven't come across prior to this course. This course is, heavy mathematical course. And it's where you get your engineering mind for math and units and dimensions and cross products and stuff all put together. All right, so let's get back to the fundamentals. Like I say, there's a lot in this course. All right. I'm going, or I shouldn't say, but I'm switching over to the other thing right now. There we go. All right. So for a second, let's go back through what I was talking about, because this is very important for you to do well in this course. So when we look at a material's permittivity, that's what this is. This is permittivity, epsilon permittivity. It's a fundamental constant for free space. There's another one called permeability for magnetism. This is for electric fields. Permeability is for magnetic fields. So permittivity, electric fields, permeability, magnetic fields. So for the permittivity of a material, and every material has, I shouldn't say well, yeah, I actually should say is a different permittivity. Air has a slightly different permittivity than outer space. It's very slightly different permittivity than outer space. But I'm getting ahead of myself, because when we look at a material's permittivity, there's two things that make up the permittivity. You have the absolute permittivity of outer space. It's called the permittivity of the vacuum, or the permittivity of free space. And that's epsilon sub 0. And then you have a ratio of that material's permittivity to the permittivity of outer space. That's what that is. In fact, you could say that if the material, like air has a slightly higher permittivity than outer space does, doesn't it? But as you can see, it's almost exactly the same, right? 1.004 as compared to 1. 1 would be the multiplying factor for outer space, because we could see that the relative permittivity of outer space is going to be 1, because it's just going to be the absolute permittivity times 1, right? Air, slightly higher. Now, you're probably thinking, well, are there any permittivities that are really high? Well, if I look at the relative permittivity of mica, that's about 5. But if I look at the relative permittivity of ceramic, and by ceramic I mean strontium titanate or barium titanate, which is the dielectric material that separates the two copper plates in what we would call a little button capacitor. You've probably seen those, maybe worked with those throughout your education here at Wentworth. You've got they look like a small little button off your shirt, and then they've got two legs coming off them, those button capacitors. The dielectric that separates the two copper plates inside those is barium titanate or strontium titanate. So those have a relative permittivity of about 9,800. Notice there's no units that I put after that, because it's a ratio. So if I had 1 meter to 10 meters, the meters would cancel out, right? It's just a ratio. So that's what we'd have here, is that the relative permittivity, and that's how we talk about permittivity for different dielectrics, for capacitors, or whatever. We talk about them in their relative permittivity. right? Because we know that the actual material's permittivity is the absolute permittivity times the relative permittivity. This has no units, it's a ratio. This has the units of farads per meter. Farads per meter. Does everyone see that? You could probably work that out yourself. What would a farad per meter? What would the combination of primary units be that would represent a farad per meter? And of course, we know that a farad is an amp squared seconds to the fourth over kilogram meters squared. And then we would divide that by a meter. And remember what happens to the denominator of the numerator? It goes down into the numerator of the denominator. I really have that m over 1, isn't it? So what we could really say here is that what these are is this going to be an amp squared seconds to the fourth over kilogram meters cubed. Right? Does everyone see that? Okay. So let's get back to Coulombs' equation. You know, the force of attraction between two like particles. And this is just for particles now. Just like this, Newton's gravitational was just for two masses, two particles. So you're probably saying, well, hey, there's something wrong here. Were they lying to us when they told us there was a Coulombic constant? No, they weren't, because what they were really talking about with that Coulombic constant is they were talking about if this was between two elementary particles, like two electrons, or an electron and a proton, or whatever. And what is between an electron and a proton? Even if the electron is zooming around an atom with a proton at the center of it, it's vacuum, isn't it? The space in between that proton and electron is vacuum. So I would have the relative permittivity. And so what they were really saying here is just like we say that the gravitational attraction is 9.81. Well, of course, 9.81 meters per second squared, but let's clarify that. That's at the surface of the Earth. If I go 1,000 miles off the surface of the Earth, I'm not going to have a gravitational attraction of 9.81 meters per second squared, am I? No, because I'm going to be further away from the center of gravity of the Earth, right? This is the qualifier too, K sub C. So we can say that K sub C, that constant that you were told, Coulomb's constant back in freshman year, would really be equal to 1 divided by 4 pi epsilon sub 0. And remember, epsilon sub 0 is 8.85 times 10 to the minus 12 farads per meter. So 8.85 times 10 to the minus 12 farads per meter times pi times 4 taken to the reciprocal gives me 9 times 10 to the 9, right? And that's how you remember it. It's actually 8.9918. Let's do that. 8.9918 times 10 to the 9. All right. And as you can see, 4 has nothing associated with it. It's just a number. Pi, just a number. Epsilon 0, though, has units associated with it, doesn't it? And as we can see, the units associated with K sub C are going to be the reciprocal of the units associated with epsilon sub 0. So we'd have kilogram meters cubed over amp squared seconds to the fourth, right? Okay, well, that's great. Now, you know, I just wanted to work through this equation that we have right here then. just to show you I should be getting units of kilogram meters per second squared, shouldn't I? Because isn't that what a force is right there? So we know that K sub C in this equation up here was kilogram meters cubed over amp squares seconds to the fourth, right? What have we got in the denominator? We've got meters squared. So if we're looking at what the units are that are coming out of here, I've got meters squared down here. Well, wouldn't that take care of the kilogram meters cubed and just leave a kilogram meter over amp squared seconds to the fourth? Right? In fact, let me just write it out here. I think that everybody can see what we'll be able to see what cancels out. So K sub C, we would have that. That would be kilogram meters cubed amp squared seconds to the fourth. And then we've got Q, so that's an amp second. And we've got Q again, so that's an amp second. So that's amp squared seconds squared, right? That's the Q1 times the Q2. And then in the denominator, we have meters squared. So how does that simplify down? Of course, we're hoping that we're going to get meters. Well, we got meters squared canceling out with all but those meters over there, right? We've got the amp squared canceling with the amp squared. We've got the second squared canceling with all but two of those. So what we end up getting in the end is kilogram meters per second squared. Doesn't that equal mass times acceleration, which equals force? I think everybody can see that. So yes, everything works out exactly fine. This is the equation that you are going to use from now on as the adult engineer, right? Not the old one that you learned in high school and that you learned in Freshman Network Theory 1. And you're probably thinking to yourself, well, my God, then, you know, if Coulombs' equation collapses to this, and it actually shows that there can be a difference in the force due to the material that's intervening between the two charges. Wouldn't there be something similar like that for gravity? And of course, now we know that's true, right? We know that there are gravity waves. We know that uh, things can change, gravitational attraction and stuff like that. Anyway, those are the two fundamental forces. I just wanted to show the analogy between the gravitational force and the Coulombic force of attraction between two different particles, right? So that's one of the first things that I wanted to do with the lecture today. And this lecture really has been broken into two pieces because I sort of paused it there at that one thing. I think I was getting a coffee or whatever and forgot to unpause it. But I want to go a little bit further. I want to explain some other things. And, you know, already one thing that you can take away from that first lecture, of course, let's just get up some equations that you're going to be using all throughout the semester. So out of that first lecture that we had, we got that c, the speed of light, is 1 over the square root of mu sub 0 times epsilon sub 0. Right? You remember me mentioning that and me saying that I was going to talk more about permittivity when we got further into the course. And of course, that's what I'm doing now. I'm talking about permittivity right here. And I brought that up in the first lecture too, of course, the 8.85 times 10 to the minus 12 farads per meter. This quantity, and I'm not saying that you should memorize this for this class. I'm telling you that this quantity, dependent upon what line of electrical engineering or computer engineering you go into, is going to be a quantity that you memorize as similar to pi, similar to the charge on an electron. And what is the charge on an electron? Minus 1.602 times 10 to the minus 19 coulombs. Let's not forget that. And of course, we got the 8.85, but let's put up here too, mu sub 0 equals 4 pi times 10 to the minus 7 henries per meter. That is another constant, and I should probably block that out too. That is really a constant that if you do work in electrical engineering, especially in communications, whether it's transmission waves or Wi-Fi or microwaves, it's going to be something that is going to be embedded in your head for the rest of your life. So you might as well just learn it right now. Now I also want to point out, and let's just take the end of this to do that. What was I going to just do? Oh, yeah, that's right. Henries per meter. Now, when we talk about mu sub 0 being henries per meter, what does that work out to be? We looked at farads per meter, and we saw that farads per meter really gives us this, amps squared, seconds to the fourth over kilogram meters cubed. That's a cube. But how about henries per meter? Now we know that a henry is a kilogram meter squared over seconds squared amps squared. And the only difference between a henry, right, the combination of primary units for a henry and the combination of primary units for an ohm, is that a henry is seconds squared and an ohm is seconds cubed. So you're probably saying, well, God, does that mean then that a henry per second is an ohm? Yes, that's exactly what it means. A henry per second is an ohm. A Weber per second is a volt. Isn't that amazing? Yeah. Anyway, let's get back to this. Henries per a meter. So that's a henry, and that would be in the numerator. And then per meter, of course, the meter would be in the denominator, right? So this gets rid of one of those. So instead of having meters cubed in the denominator like we did for permittivity, we end up getting kilogram meters per second squared amps squared. And you're probably saying then, well, isn't mu sub 0? Anyway, you can, I love working with units and dimensions, and that's what dimensional analysis is really all called. And that's what you want to look into throughout your life too, as you're going into experimental work, is dimensional analysis and similitude. You get that in mechanical engineering, but we have so many courses in electrical engineering that we have to take that, we can't get a really good course on dimensional analysis and similitude. Anyway, back to this. So we have this one equation right here. That's a fundamental equation. We're going to look at that. In fact, we've got some other equations that I want to put into this lecture too. Here's an equation you're going to be using throughout the semester. Frequency times wavelength. Right? Let's just think of a wavelength, right? So if we have a wave, right, that's moving, well, naturally, the frequency times the wavelength is going to give us the velocity of propagation, right? So we'll go more into that too. But right now, this is I'm just trying to list a lot of important equations. The velocity of propagation, by the way, and I'm going to derive this equation. I'm just going to give it to you now. I was thinking about, God, maybe I shouldn't give it to him, but the velocity of propagation is really the speed of light divided by the square root of the permittivity that waveform is traveling through. Now, I'll derive that a little bit later, I just want to give you a bunch of equations that we're going to be seeing throughout the course of the semester and how that's going to affect really how we're going to determine different materials' permittivity is to find out how slow they go inside the material, right? We'll be doing a lot of things with that. We also have distortion, a lot of other things that we're looking at. I also want to just sort of flash ahead to fiber optics, because at the end of this course, I'm going to probably be talking a little bit, maybe introducing a little bit about fiber optics, if we have enough time to get through all of the other tremendous amount of material that we're going through in this course. I also realize that this course is only lecture and it's not lab, so you know, we'll see. So for fiber optics, the velocity of propagation is not the speed of light divided by the relative permittivity. That's for transmission lines. And that doesn't matter if it's a transmission line that is transmitting 60 hertz, you know, voltage, a 60 hertz waveform, or something that is transmitting radio frequency, like a coaxial cable. So there's no difference between those two. We have equations for that. But when we're talking about light traveling through a fiber optic, the velocity of propagation there is the speed of light divided by the index of refraction. Okay? So we're going to be talking a little bit about that at the end of the semester too, getting into fiber optics. And what was the other thing I wanted to finish off with this lecture? You know, really, the next lecture is going to be a review of vectors, because we're going to have to, you know, everyone's going to have to be up to speed with dot product and cross product. And I know that you learned all of those in engineering mechanics. I'm just not sure in looking at the class list if everybody had me for engineering mechanics. So I'm going to just do a review over that. Some people may have questions, but you know, we've got a whole section in the book on vector operations too. So I'm going to refer you to that. I think I'm going to hold it there now. And then, like I say, the next lecture is going to be on vectors so that we can start to bring this all together. There are two other forces. These are nuclear forces. I'm just going to, like, you know, 1 minute lecture, nuclear forces that we know of. There's the weak nuclear force, and there's the strong nuclear force. Now, neither of those two forces are really going to be coming up in this class, but I just thought I'd mention those two and tell you really what they are. The weak nuclear force, and really the weak nuclear force is also connected with the electromagnetic force, and they've found a unified theory now for electroweak force. That's what we call the we could really say that there's like three manifestations of forces now: gravity, electroweak, and the strong force. The strong force is what holds quarks together. The weak nuclear force is a force, sort of almost an adhesive force, that holds protons together and neutrons together inside the nucleus of an atom. Okay? So maybe if I have more time, we can talk more about that. But I'm going to end this recording right now, and this is, I guess, the fourth lecture, and we'll, you know, keep going. All right.